Okay, so let me bring this down so you can read it. I think problem 31 is actually quite a quick little problem. I wrote it out sort of verbosely because I'm not quite sure where people are getting confused on this. So let's recall the setup. So we say that a permutation sigma moves an element A. So this is a permutation sigma. This is an element of S. Oops, my little element symbol is not working. S sub A. So it moves an element of A if sigma of A is not equal to A. Another way of saying that is it moves an element if that element is not fixed by the permutation. So let's let A be an infinite set. And let's let H be the set of all permutations in the group of permutations on our set, such that the number of elements moved by sigma is finite. Let's show that H is a subgroup of the group of permutations on A. So what do we need to do to show that it's a subgroup? Well, first of all, we need to show that it's closed. So any product of any two elements in H is still in H. We need to show H contains the identity, and that for all elements in H, we have the inverse also in H. So it has inverses. So to see closure, let's take two elements in H. These are, remember, two permutations in a group of permutations on infinite set. But these are special permutations. These are permutations that move only a finite number of elements. So sigma in particular, just a random permutation from H, moves a finite list of elements in A. Let's just label them. It's a finite list, so it's going to be a natural number as the number of elements here. So A1, A2, A3, dot, dot, dot. However many it moves, we know it's finite, so this is a finite list. Similarly, if we take another permutation that's in H, it moves a finite number of elements as well. And we can label them, let's just call them B1 through Bm. So may or may not, M and N may or may not be equal, but we do know they're both finite and they're both integers. These lists can certainly overlap, but the key observation here is that all the elements of A not in the set, so not in the set of elements that are moved, are fixed. So for each one of those, so for an element not on the list for sigma, so sigma of k is equal to k, I shouldn't have used k, but if k is not in this list, here. Right? So everything else is fixed, except for the finite number of things that are moved. So if I collect up as a set all the elements moved by sigma and all the elements moved by tau, it'll be a finite set of elements. In fact, n plus m elements. Everything else is fixed by both sigma and tau. So in other words, sigma and tau don't move anything that's not in this set. And so the product can't move, the product sigma times tau or tau times sigma can't move anything that's not on this list because they fix all the other elements. In particular, that's a finite set, so they move only a finite, so the product moves only a finite number of elements. So H is closed. If I take two elements from H, I multiply them together, I still get an element from H. To see that the identity is in H, recall how the identity on permutations works. It moves no elements, right? It takes each element to itself. So there's no element of A that satisfies the defining characteristic here. So it doesn't move anything. So it moves 0 elements. 0 is a finite number, so the identity is in H. So to see that the inverses are in H, notice that sigma inverse can only move the same elements as sigma, and you should convince yourself as to why that is. Maybe do a quick contradiction proof and break up sigma and sigma inverse into transpositions and show that if, for example, sigma inverse has a transposition that contains an element that's not in sigma, that it won't be the inverse of sigma. So you should at least think it out and maybe even write down a proof as to why that's true. But that means since sigma moves a finite number of elements, then so does sigma inverse. So in particular, if sigma is in H, then sigma inverse is in H. And now we have closure, we have inverses, and we have the identity. So we have that H is a subgroup of S sub A.